In this video, we're going to learn about the Bohr model. Now, the Bohr model is a model of something that you'll never really be able to manipulate yourselves, right? The atom is so small. So I think to begin with, we should see the similarities between the Bohr model and just the moon revolving around Earth. If you look at the moon, right, it's never going to hit Earth. It is attracted to Earth because the moon has mass and Earth has mass, and those masses attract each other. But the moon does have a certain amount of speed, causing it to move around in a circle as the gravity is still pulling it in, but it's still moving on its own. And similarly, we can say that there's attraction between the positive nucleus and the negative electrons in an atom. There's attraction there, but the electron is still moving tangentially to that attraction in the atom. Now, this isn't exactly how things work, as was later determined by Einstein and Schrödinger and Heisenberg and all the quantum mechanicists, but Bohr was able to make a really, really useful model around this. So what Bohr found is that electrons can exist in specific shells with discrete potential energies, meaning that an electron can exist in this first shell, or the second, or the third, or the fourth, fifth, sixth, seventh, or eighth, but never with, never the 1.5 energy level. There are specific energy levels that are possible. An electron can have this much energy, or this much energy, or this much potential energy, or this much potential energy. Very much like you can be on the first rung of a ladder or the second, but you're not going to be in between them if you're climbing a ladder. Now, I will point out that although ladders have exactly the same gap in their rungs continually, or at least they should, in the case of atoms, their energy levels get closer together as the energy level gets higher. You can see the gap between 1 and 2 is big, 2 and 3 is smaller, 3 and 4 is smaller still. Now, how did Bohr figure this out? It's actually quite brilliant. What he did was he took a bit of hydrogen gas and put it in a discharge tube where he ran electrical current through it. And what this did was it caused electrons in the hydrogen to jump up to higher energy states. Now, he didn't know this, but what happened next was, what goes up will come down. There were electrons that would jump from whatever higher energy state down to lower energy states. And those that jump down to the n=2 state, the second level, they would release a certain amount of energy that's in the visible spectrum. If an electron went down to the first shell, it would be in the ultraviolet region and we wouldn't be able to see it. So Bohr wouldn't notice. But and also, if an electron went down to the n=3 shell, it would have been in the infrared, which is also not something that we could see with our eyes. But Bohr did see that electrons were falling down to lower energy states and causing a release of energy in the visible spectrum. But instead of it being that all possible wavelengths of light were emitted, there were only specific energies that were emitted. And these energies corresponded to the gaps in energy of the different energy levels. For example, if an electron was in the third shell and dropped down to the second shell, that is not a very big gap. That's a low energy change. And so the light that was released going from the third shell down to the second had a wavelength of 657 nanometers, which is a long wavelength, meaning low energy. And that is very much consistent with the fact that we're only going from the third down to the second shell. When an electron went from the fourth shell down to the second shell, this is a bigger gap in energy. And so there would be a shorter wavelength corresponding to a higher energy gap. And finally, in the case of the violet at 434 nanometers, this was highest. The highest energy photon was violet, and that corresponded to the highest change in energy level from the fifth down to the second. So again, if it were that electrons did not exist in these specific shells, if there were like an electron that's here, a little bit above the third shell, going down to the second shell, if that were possible, then this would be a slightly greater energy than the n equals 3 to n equals 2. So, we'd see, instead of 656.2 nanometers, we'd see something a little bit lower than that, but we'd see another one. And then if we had an electron coming from slightly higher down to here, we'd have another photon just a little bit further to the left. But instead of getting this continuous spectrum where we have every possible energy gap, no, there are only specific energy levels that are allowed for electrons to have. So, as I mentioned before, it was the visible spectrum that was noticeable to Bohr. So we saw energy released, we saw photons released in the visible spectrum that corresponded to electrons jumping down to the second shell. And that's what we're seeing here in what's called the Balmer series. If we were to consider an electron going down to the n equals 1 shell, even if it was the smallest gap there, the second shell to the first, that's 122 nanometers. That is very much in the ultraviolet range. So even that gap is something we would never be able to see with our eyes. It's something that is emitted, just we can't see it with our bare eyes. Similarly, there's the Paschen series where the the electrons end in the third shell. And even if you have an electron going from the n equals 50 shell down to the n equals 3 shell, it will be too high a wavelength, too short, or too low a frequency, and too low an energy to be visible. It would be in the infrared range. So let's solve some problems here. Hydrogen's electron in the ground state absorbs a photon with a wavelength of 95 nanometers, causing the electron to rise to the n equals 5 shell. The ground state means that it's in the n equals 1 initially. So if I ask the question, what's the difference in potential energy between hydrogen's n equals 1 and n equals 5 shells, I can answer that question. What we're looking at is this, an electron going from this first shell up to here, right? And all right, so if we're trying to figure out this energy difference, what we can say is that the energy is equal to the energy of that, or that change in energy, I should say, the change in energy from the first to the fifth shell is equal to the energy of the photon that is required to make that happen. So the change in energy from n equals 1 to n equals 5 is equal to the energy of the photon that is absorbed, which is equal to hc over lambda, which is equal to 6.626 times 10 to the negative 34th joules times seconds, times 3.00 times 10 to the 8th meters per second. That's our C. And we're going to divide that by, if we want to convert 95 nanometers times 1 meter over 10 to the 9th nanometers. The nanometers cancel. We end up with 9.5 times 10 to the negative 8th meters. And that's what we'll put here in the denominator, 9 0.5 times 10 to the negative 8th meters. Cancel out the meters, cancel the seconds. We end up with energy in joules as we're expecting, and that energy is equal to, I have this written down, it's going to be equal to 2.09 times 10 to the negative 18th joules. And that is the change in energy as we go from the n equals 1 to the n equals 5 shell. So, next question is, in order to raise the electron from the ground state to the n equals 4 state, would the required wavelength be greater than, less than, or equal to the wavelength required to raise to the n equals 5 shell? Well, if we're only going to the n equals 4 shell, then there's going to be a smaller energy, which means that there will be a longer wavelength. So it will be greater than the 95. And if the hydrogen electron drops from the n equals 5 shell down to the n equals 1 shell, important point to note is this is the opposite. So in the previous case, we're talking about taking a photon of light and shining it on the electron, and the electron absorbs the energy from the light and raises to a high level. Well, going in the opposite direction, if we have an excited state electron in the n equals 5 shell and it goes down to the n equals 1, then it will release a photon. It will emit a photon, and that photon will have exactly the same energy as the photon required to make it raise to the n equals 5 shell. It will be this one here, that 2.09 times 10 to the negative 18th joules, which corresponds to a wavelength of 95 nanometers that we started with. And so the answer to this question, is it visible? No, it is in the ultraviolet range, because UV is less than 400 nanometers and 95 is less than 400. I hope this video has been helpful. Let me know if you have any questions or comments in the comments section. Thank you.